Hey everybody, it's Mr. Francis, and got a quick video for you for review for Chapter 9. Okay, so Chapter 8 focused on calculations with the mole, and we saw all that. So now we're going to take this a step further. We're going to take that mole calculation, the relationships that we saw with the mole, especially molar mass, and now apply it to a balanced reaction. And the thing I want to remember, when we were balancing chemical reactions, we used those coefficients. And one of the things at the time we said the coefficients, as you can say here, the relative number of molecules. Well, we can take that a step further. Again, know the definition of a mole. 1 mole of any substance contains 6.022 times 10 to the 23rd atoms or molecules of that substance. So in the above equation here, yeah, each of the coefficients are going to tell us, hey, we've got 1 molecule of ethanol, 3 molecules of oxygen. Well, instead of looking at a single molecule, let's take those same coefficients and now apply it to the mole. So 1 mole of ethanol, 3 moles of oxygen, 2 moles of carbon dioxide, 3 moles of water. So each of the coefficients now are telling us the number of moles for each of the substances, for that respective substance, in the reaction. So you look at this equation, which is balanced for us. So again, if we're looking at the coefficients, that's telling us, hey, we've got 1 mole of carbon sulfide, 2 moles of the carbon oxide, 6 moles of oxygen, and a mole of sulfur dioxide. So you look at this aspect. Hey, if we look at this in terms of dozens or in terms of moles, again, go back to the reaction, we're just looking at the coefficient in front of each of the substance. So in this case, since we're working with copper, hey, we can look at this as 6 moles of copper or 6 dozen copper atoms. The relationship is going to be important. It is what we call a ratio. And it's that mole to mole ratio that we can use to allow us to convert from one substance to another. And this is going to be the key as we look at these calculations. Can you look at a balanced equation and find the mole ratio between two substances? And in doing so, hey, all you're looking for is that coefficient between the two. So here's this reaction. And here you can see the question. How many moles of the sodium fluoride will be produced if 3.5 moles of sodium is used? Okay, so we're going to look at the relationship between sodium and the sodium fluoride. And look how they broke this down. Again, asking questions that we know. What's our given measurement? In this case, the 3.5 moles of sodium. What are we looking for our answer? The moles of sodium fluoride. We have that information. Look at how they put this together. Here's that mole ratio, and all we're using is the coefficients in front of each of those substances. And then we do the math. We can stretch this out. Again, same aspect here, same equation. And again, we're asking those same first two questions. What's our given measurement in the units? What's the units for our answer? In this case, our given measurement, the 3.74 moles of propane. Our answer, the moles of carbon dioxide. And you can see how that's put together. Again, note this mole ratio, set up the same way. The given units are on the bottom, the units for the answer on the top. If we include masses in here, now the only thing that we're going to do with the step is we add in our molar masses. And that's stoichiometry. So here's our problem. And again, this is actually a balanced equation now. The chromium plus oxygen to form the chromium oxide. And again, look at this. We start with 15 grams of chromium. We want to find out how many grams of the chromium oxide gets produced. We've got our equation, our information. Look at how this is set up. The 15 grams of chromium, we convert it to moles of chromium. The moles of chromium, we convert to moles of the chromium oxide. Again, there's that mole ratio. And then finally, the moles of chromium to the grams of chromium oxide. And you can see how that's all put together. So this calculation is really no different. And that's the thing with stoichiometry. It's the same 3 calculations each time. Molar mass, mole ratio, molar mass. You see the exact same thing, same problem. The only thing we've done, we've changed our chemical equation. Molar mass, mole ratio, molar mass. That's what you're going to see for the calculations and the answer. And again, same thing. Molar mass, mole ratio, molar mass. And we get our answer. What's going to be important on your part? Answering those first two questions. What's the given measurement in the units? What's the units for the answer? And here, they take this a little step further because now we want to identify X. But again, mole ratio, and then put that together. Hey, we solve for carbon. We can take this a step further. The idea of a limiting reactant is that in every chemical reaction, one of the reactants gets totally consumed. So here's this reaction between nitrogen and hydrogen to produce ammonia. Here's the reaction, here's the combination, but look what happens after the reaction's done. You see the mixture here. Here's the combinations. We've got some excess product. We got some of the excess reactant left over. So there's always going to be one reactant used up, one that remains. And that's what it says here. The reactant that runs out first, it limits the amount of the products that can form. That's going to be key. Here's this reaction. So methane and water produces hydrogen and carbon dioxide. So if we were given starting amounts of these two, find a product, we want to determine, okay, which one of the reactants is that limiting reactant. And you can see in this case, the combinations involves, hey, water's being used up first. The water is our limiting reactant. Okay. There's two approaches. I'm going to skip approach A. I'm going to go to approach B because I actually like it better. To solve a limiting reactant problem, again, you're going to have the balanced equation, but I like this step. We're going to do the first two steps. We're going to do the first two steps in the stoichiometry calculation. So you're going to do the molar mass calculation and then the mole ratio. And then this right here. This is the step I want you to remember. The one that's the least number of moles. So here's our example. A and B are reacting together. They give us our equation. Okay, so we do the first step. We convert our gram amounts to moles. We do our second step. We convert each of the mole amounts to mole amount of our product. So again, remember what our answer is. Our answer is going to be the least amount of moles. In this case, 0.33. So we'll take that 0.33 and multiply it times its molar mass to get our grams. And we would do the same thing here. Here's this reaction. So what you want to do is you will want to do the calculations, moles for each of the products to find that out. And again, the same thing with this concept. Set up for each of the two reactants. In this case, you're in moles, so do that step, the mole ratio. You get your answer. Here's this problem. Again, we're going to take the 3 grams of nitrogen, 3 grams of hydrogen, convert each one to ammonia. We'll go grams of nitrogen to moles of nitrogen, moles of nitrogen, moles of ammonia. Same thing for the hydrogen. Again, whichever one gives us the lesser amount of moles of ammonia, that's our answer. And then we can convert it to grams. Percent yield is actually a very simple calculation. The actual yield is what you would do when you actually do the work, and it is what it's what you do in the lab. The theoretical yield, that's what you calculate. And that's what they talk about here in the definitions of each. And you just divide the two. Multiply it times 100, you get your yield. You're always going to be given the actual yield. So in this case, hey, we calculated, go back a couple slides, we calculated the 8.33 grams of C, 7.23 divided by that, and we get our percent yield. And you can do the same thing with this problem. Again, you get Here's your actual yield. So just do the conversion, 1 gram of oxygen, how many grams of sulfur trioxide does it produce? And you can get your percent yield. And the same thing here. Now we're going to reverse this a little bit. We give our yield. We want to produce this much. So we're going to take this total, this 85.0 grams, multiply it times that 64.9. That's going to give us what our theoretical yield would be. And then we can work backwards, take the theoretical yield, find out how many grams of phosphorus we would actually start with. If you got any questions, feel free to contact me. But this was just a quick review. Good luck. I'll talk to you soon.